Okay, so this is MTH 449, Probabilistic Number Theory. Okay, so we are familiar with probability and we are familiar with number theory. This subject is a very interesting interplay between two topics in mathematics, as you would have guessed from the name, namely probability and number theory. So, the aim is to learn techniques to address problems in number theory with the help of probability theory by interpreting problems in number theory in a probabilistic language. But that is not the only thing that we learn. We also learn the other way round, meaning there are some questions in probability which can be addressed by number theoretic techniques, or certain concepts in probability which can be expanded or better understood by the framework provided by number theoretic techniques. So, this course is essentially about the relationship between the two, and of course, I am going to sneak in a lot of number theory while doing this. So, now the subject of number theory is a very wide subject. It is like a fortress, and how do you get into the fortress? There are many different paths. So, the path that we primarily take is the analytic path. So, what does this mean? Analytic number theory essentially is the use of real and complex analysis to study what are called arithmetic functions Okay, and what are arithmetic functions? Arithmetic functions are functions whose domain is the set of natural numbers and which could possibly take complex values. In other words, these are basically sequences, and we want to study the behavior of the sequences, and when I say behavior, it means various concepts, for example, growth of a sequence, with the help of real and complex analysis. Now, certain arithmetic functions are basically functions on the real line in disguise, right. So, let me just give you a brief overview of some useful arithmetic functions and how they are studied with the help of analysis. So, let us take, suppose, let us take something which is very well understood. In fact, you learnt this technique basically in your first year calculus. So, suppose you have, let us start with real valued functions which are defined on the real line, okay, and suppose such a function is monotonically decreasing on some interval, let us say on an interval 1 to n, where n is some natural number. Later we can also replace it by some real number. This is just to keep things simple. So, here is the situation. You have some nice real valued function. Let us also assume that it is continuous. Okay. Because of these conditions, it is very easy for you to draw a graph of such a function. let us say at least in the interval 1 to n, you know that the graph is monotonically decreasing. So, now suppose I ask you to study the function at natural numbers. So, in particular I want to study the average or the sum of the function values. So, suppose I put f of I, okay, I going from 1 to n, f of 1 plus f of 2 and so on till f of n. Suppose you want to study this, okay, and if you divide that by n, you are basically asking what is the average value of your function f when you see it as an arithmetic function in the interval 1 to n. So, you learnt from your integral test what was the basic idea. Let us, for fun, let us just review it. So, you have basically what you do is you form rectangles of breadth 1. Okay. So, here the breadth of each of these rectangles is 1, and let us say you have a rectangle whose length is f of 2, then you have another rectangle whose length is f of 3, and finally you have, okay, you have a rectangle whose, so let us say your okay, length is your f of n. So, what is happening is you can write this as f of 1 plus f of 2. So, what is f of 2? F of 2 is f of 2 times 1, which is the area of this rectangle. F of 3 is the area of the next rectangle, and so on and so forth until you hit the last rectangle, and you observe that the sums of the areas of this rectangle is certainly less than the area under this curve from 1 to n. Okay. So, this is equal to, this is certainly, okay, so this is I going from 2 to n f of I. So, keep f of 1 intact, okay, plus what do you have? This is simply the area under the curve of the function f of t dt from 1 to n, right. So, what have you done? You have very nicely converted this sum into, you have bounded this sum by an integral. Now, you can play the same trick to find a lower bound for this sum. Now, what you will do is you start from 1. So, you draw a rectangle, the first rectangle will have length f of 1, then the next would have length f of 2 and so on, and then the sum of the areas of these rectangles would be greater than the area under this curve. So, you get an inequality in the other direction. Okay. Of course, you have to pick out a couple of values and bring them out of the sum first, but you get the general idea. And more generally what we have is that suppose you have two natural numbers a and b, okay, with a to be strictly less than b, and let us say that f of x is a monotonically decreasing or a monotonically increasing function. The same kind of analysis can also be done when you have a monotonically increasing function. You can draw a bunch of rectangle and compare the integral with the areas. So, I am going to club them all in a general framework. Okay. On the interval a to b. Okay. Then it turns out, I am going to leave this as an exercise for you, it is just a generalization of what we did here. The minimum of f of a, f of b plus integral a to b f of t dt will turn out to be less than summation I going from 1 to not 1 sorry a to b f of I, and this will further be less than or equal to the maximum of f of a and f of b plus the integral f of t dt. So, this is basically your integral test from your first year calculus, isn't it? And what does it tell you? If you are trying to understand the growth of this sum, you are essentially translating it into the problem of understanding this integral, which is easy to study because this is a continuous function and monotonic. And as a result, as in one of the first few consequences that you would have learnt of this, you can take a to be equal to 1 and b to be equal to some natural number, say n, and as you let n go to infinity, this integral test tells you that summation n going from 1 to infinity 1 over n diverges, whereas if you take summation n going from 1 to infinity 1 over n raised to the c, where c is anything, any real number strictly greater than 1, this sum converges. Okay, but this all this you have learnt before. One other amazing consequence of the integral test, which will be expanded in the exercise and we will also discuss it in our live session, is that summation 1 over p, where you run over all the primes, this diverges, this sum does not converge. And therefore, this is another way of deriving a fundamental fact that there are infinitely many primes. This is, in other words, this is an analytic way of viewing the fundamental fact that there are infinitely many primes, because had there been just finitely many primes, this sum would have converged. All right. So, we will discuss this more. So, just at even with such an elementary technique, we have derived a very beautiful fact, namely the infinitude of primes. Now, all functions are not of this nature. Obviously, there are very few functions which can be categorized in such a neat manner. So, we want to learn different types of techniques which would help us to address the study of a larger class of arithmetic functions. So, what do we do? Here is the next technique that I would like to address. Again, in some sense we will keep our functions to be suitably nice, but we will ignore the condition of monotonicity. We will not need it. And you will see how this technique divulges some very nice information about the study of prime numbers. Okay. So, here is the idea. So, let us take a function which is defined on the set of real numbers, and now we do not have to restrict ourselves to real valued functions because we do not worry about monotonicity. We could take complex valued functions as well, but we want the function to be nice. What does it mean to be nice? Is something that we will specify as we go on with our calculations. Okay? At the very least, nice definitely means that the function is differentiable. Right? So, what are we trying to do? So, we want to study the sum I going from 1 to n f of I, okay, where n is some natural number. In fact, more generally, we do not even have to, okay, for now let's take n to be a natural number, but we can replace it by, instead of writing I going from 1 to n, we can replace it by f of I, as I is less than or equal to some specified real number. More generally, instead of just looking at these values, we can attach, our technique is broad enough for us to be able to attach certain weights to these functions, right. So, this is what we do. So, let me just take, okay, to start with, just to keep the framework easy, and then I will tell you how to enhance this. So, I want to study two product of two functions u of n and f of n, where f is this function which is defined on the real line, and u of n is another arithmetic function which we know, which we define, which is defined in such a way that we know that what the values are for natural numbers. We need not have u to be defined on all of R. We want to take something that is defined on the set of natural numbers. So, this is an arithmetic function. F is also an arithmetic function, but it is something more than an arithmetic function. Okay. So, now what we do is we denote capital U of t to be equal to summation n less than or equal to t little u of n. So, partial sums of little u of n for all those n's which are bounded above by some number t. So, this is your basically your partial sums u of t, and now we want to look at this sum n going from 2 to n little u of n f of n. I want to be able to reduce the study of this function into the study of u of t and f of t. Somehow when you combine, let us say you know something about u of n, the partial sums of u of n, and you know something about the functions f of n, how do you combine them to derive bounds for these weighted sums? So, let us take this, and this is actually looks like I am pulling something out of a hat, even though it is actually a very elementary fact, but the reason it feels like we are pulling it out of a hat is we do not know why we are doing this. So, what am I going to do? Little u of n, I am just going to replace it by capital U of n minus capital U of n minus 1 times, so this term times f of n, right. Notice capital U of n minus u of n minus 1 is just exactly equal to little u of n. Now, we separate these sums out. So, we have n going from 2 to n, capital U of n f of n minus n goes from 2 to capital N, but you have u of n minus 1 and f of n. So, I am just going to make a change of variable and let n go from 1 to capital N minus 1. So, whatever we are now left with, capital U of n times f of n plus 1. Now, there are many terms here, summands which match, but some terms do not. So, we take this out. So, what do we do? So, this sum is going from 1 to capital N minus 1, and this is going from 2 to n. So, from the first sum we take out capital N. So, let us write u of capital N f of capital N. Okay. From the second one we remove little n equal to 1. So, what are we left with? U of 1 times f of 2, okay. And then we have summation n going from 2 to n minus 1 u of n times f of n plus 1 minus f of n. And now we start specifying what the niceness means. Suppose you knew that the function f is differentiable. Not only that, suppose you knew that the function is differentiable and the derivative of the function is continuous in the interval little n to n plus 1, okay, for every n lying between 2 to capital N minus 1. So, then this turns out to be equal to u of capital N times f of n minus u of 1 f of 2 minus summation n going from 2 to n minus 1 u of n times the integral n to n plus 1 f prime of t dt, provided, let us specify this as I just mentioned, our function f is continuously differentiable on the interval 2 to capital N. What do I mean by continuously differentiable? It is differentiable and the derivative is continuous. On the interval 2 to n. With that in place, there is another simplification you can make, which is as follows. This sum will turn into u of n times f of n minus, you have u of 1 times f of 2 and then this remaining sum, you can do another little trick. Notice that u of n, this function remains constant in the interval n to n plus 1, open at n plus 1. So, for any t lying between n and n plus 1, u, capital U of n is equal to capital U of t. The only problem is when it hits n plus 1, that is just one point in this domain of integration, and so it will not affect our final result. So, we can actually move this u of n inside the integral, and what we end up getting is n going from 2 to n plus n minus 1 u of t f of f prime of t dt. And what is this equal to? U of n f of n minus u of 1 f of 2. By the way, capital U of 1 is just little u of 1, there is nothing big happening there, minus, and now we unfold this integral from, so start from little n equal to 2. So, first you have 2 to 3, then 3 to 4 and so on till n capital N minus 1 to capital N, and therefore, we unfold this integral to get something from 2 to n u of t f prime of t dt. So, again we are using the analytic property of your function f to convert a sum, a weighted sum, into basically an integral. And this trick can be generalized in the following way, and this is what is called the Abel's partial summation formula. It has two forms, we will write both, they are essentially equivalent to each other. So, what is this formula? It says the following. Let us take non-negative real numbers x and y with y to be strictly less than x. Let u be some arithmetic function, okay, and f be a nice function in the interval y to x. So, f be a function differentiable on the interval y to x. Then, if you want to study the sum, the discrete sum over natural numbers which are strictly greater than y and less than or equal to x, u of n times f of n, this has a very nice form. This is basically equal to capital U of x f of x minus capital U of y f of y, okay, minus integral y to x of capital U of t f prime of t dt. So, you have converted a sum into basically an integral, and the form in which this summation formula is used for many applications is a little more is a special case of what we just wrote down. So, let me also specify that. In particular, you can suppose you want to take all the natural numbers up till x. Okay. So, the other form, a consequence of this. So, this is your general partial summation formula, and as a corollary to this, suppose you have, let us have a function be continuously differentiable on the interval 1 to x. So, basically I am just taking little y equal to 1. Now, this sum is starting from n is equal to 2. if you are taking y to be 1, since n has to be strictly greater than y, this little technical detail is important. Okay. And then you are left with, you on the right hand side you will have capital U of x, f of x minus capital U of 1 times f of 1 minus this nice integral that we do not have to do anything to. So, what we do is this term U of 1 times f of 1 can be moved to the left hand side. Okay. Remember, capital U of 1 is exactly equal to little u of 1. So, what we end up getting is that if you run over all the natural numbers up to x, little u of n, f of n, this is equal to u of x, f of x, even if x is some real number. This our previous technique can be generalized to the situation when capital N is some real number, not just some natural number, minus integral 1 to x capital U of t f prime of t dt. Okay, so, this is the first major technique that we are learning in this course, and over several lectures you will see many interesting applications. So, this particular equation is often referred to as the technique of partial summation. Let us apply this to the study of prime numbers. So, let us do the following. You see the advantage of this technique is basically that it helps us to convert very abrupt and raw counting functions into a smooth form. For example, the function that is of great interest to number theorists is the prime counting functions, pi of x, which is defined as the number of primes p less than or equal to x. Okay, which, so what you can do is, so you can define, let u of n to be equal to the following arithmetic function. It takes the value 1 exactly when n is a prime number and 0 otherwise. So, 1 when n is prime and 0 otherwise. This is an arithmetic function, and your pi of x is basically summation n less than or equal to x u of n. Now, what we do is we take the function, we want to relate, we want to somehow smoothen out this counting function and then apply other techniques to study those smooth forms. The moment you change an arithmetic expression, by an arithmetic expression I essentially mean a counting function, into a smooth sum, then there is a very wide variety of techniques that you can bring in to study that smoothened sum, and then it gives you information about the original counting function that you had. So, here is the situation. So, I define this, you have the prime counting function pi of x, and then you also have a function which you call theta of x, which is summation p less than or equal to x. We attach the value logarithm of the prime to each prime. Okay. So, we want to somehow relate these two functions, and for that we observe that if you define f of x to be equal to log of x on the set of all real numbers greater than or equal to 1, for example, then what you have is that your theta of x is equal to summation n less than or equal to x u of n times f of n. So, I am just rewriting this smoothened form in a way that makes the application of the partial summation technique immediate. So, what do you get by our the theorem that we wrote here? Notice your function f of x equal to log x is obviously it is continuously differentiable on the interval 1 to x. So, what we can write this as u capital U of x. So, this is just the partial sum n less than or equal to x u of n, which is exactly the prime counting function. So, pi of x times f of x, which is log x, minus integral 1 to x capital U of t. So, your prime counting function pi of t f prime of t dt, which is just, so what you end up getting inside is pi of t over t dt. So, this is a very neat form, a neat expression which expresses this theta of x in terms of the original prime counting function. We can invert this now and apply partial summation again to do the opposite. Write pi of x in terms of this expression theta of x and then draw equivalences between the two. So, what do we do now? Now, what we do is we make the following observation. Your pi of x is basically your summation n less than or equal to x u of n f of n over f of n, right, f of n being equal to log of n, right. So, now what we do is we apply the partial summation technique to the arithmetic sequence u of n times f of n and the function 1 over f of x, but now we have to be careful because at x equal to 1 this is not defined. So, instead we start with the interval 3/2 to x. So, we are going to apply the original form of the partial summation formula to the interval 3/2 to x. So, what are we doing? So, we take capital F of x to be equal to 1 over log x and observe that this is continuously differentiable on the interval 3/2. Okay, let me just say f of t 1 by log t is continuously differentiable on the interval 3/2 to x. So, and then the arithmetic sequence you take is, so let us call this capital A of t is just defined as summation n less than or equal to t u of n f of n. Instead of just taking the arithmetic sequence u of n, you are taking the product u of n times f of n. So, what do you get by applying the partial summation formula to this? So, this tells us that pi of x is equal to capital A of x times capital F of x, which is 1 by log x, okay, minus capital U of y. So, here our capital U is actually capital A, since this is the arithmetic sequence that we are taking. Okay, so, we have A of 3/2 over log of 3/2, but notice what is this? This is actually, it takes the value little u of n takes the value 1 when n is a prime. Now, below 3 by 2 there are no primes, right. So, this is just 0. So, although we wrote this term, it is actually not there, okay, minus 3 by 2 2x of capital U of t, which is capital A of t in this particular example, times f prime of t, capital F prime of t. Okay. So, what the derivative of capital F prime of t? I am sure you can find the derivative of this. So, what do you end up getting? So, plus 1 over t log t whole square dt. But then your capital A of t is just your original the theta function, right. So, this is, so what you end up getting is that your pi of x is equal to theta of x over log x minus plus, this is just 0, integral from 3 by 2 to x, okay, theta of t over t log t whole square dt. And in fact, again, because for t less than 3 by 2, this theta of t is just 0. So, you can in fact just replace this with 1, it does not matter. So, you have got a function which converts pi of x into theta of x, and you have an equation that converts theta of x into pi of x. And therefore, this is extremely important for us in the study of prime numbers. By combining these two equations, what we end up getting is two different forms of what is famously called the prime number theorem. So, what is the prime number theorem? It is a very important theorem in the study of distribution of prime numbers. So, I will indicate over the next few lectures, we will learn techniques which will lead to a complete proof of this theorem. So, this was a conjecture that was first made by Gauss. So, what does this theorem say? It says that the limit as x goes to infinity, pi of x, the prime counting function, log x over x, this limit is equal to 1. In other words, your pi of x is asymptotic to x over log x as x goes to infinity. The value of pi of x comes closer and closer to x over log x as x becomes larger and larger. This is the prime number theorem. And what partial summation tells us is that it tells us the following. The above asymptotic holds if and only if a related asymptotic holds for theta of x. So, this is equal to 1 if and only if limit as x goes to infinity theta of x over x is equal to 1. So, to say that pi of x is asymptotic to x over log x is equivalent to saying that theta of x is asymptotic to x, all right. So, this I leave as an exercise for you. You can use both the equations that we derived using the partial summation technique to derive this equivalence. It will not give you the prime number theorem, but it will tell you that the prime number theorem is equivalent to the assertion that your theta of x is asymptotic to x as x goes to infinity. Now, there is another related function to this theta of x, which can also be used, and in fact, which is used to study the prime counting function. You have pi of x, you have theta of x. Now, I also introduce another function, which is the following. So, it is the following arithmetic function lambda of n, which is defined as the function log of p each time your n is a prime power to the k, that prime being equal to p. If n is equal to p raised to the k, this is equal to log p and it is 0 otherwise. Okay, so, recall your other the function that we just we were looking at, this log p. So, the other let us call this t of n, okay, which is just u of n times f of n in our previous language. This was log p when n is equal to p. Each time n hits a prime, you get the value log p, whereas in this previous function, each time n hits a exact kth power of p, you take the log of that p. So, at the outset, it looks like this function is capturing many more values than this, and we wonder whether asymptotically the sum lambda of n as n less than or equal to x behaves, is the behavior much worse than theta of x, for the simple reason that there are many more values being picked up, right. That is our concern. By the way, these functions are usually denoted as, they are called von Mangold, named after the person who first defined and studied them, as a means to study the distribution of prime numbers. Okay. So, you will see in the literature lambda of n, when people are in general, when they say von Mangold function, they are usually referring to lambda of n, but actually both of these are named after von Mangold. So, the question, as I just mentioned to you, is what is the relationship between summation n less than or equal to x t of n, which you have originally defined as theta of x, and the summation, the partial sum lambda of n, which you define as psi of x. Is this sum really much bigger than this sum here? So, let us write this down. So, psi of x is equal to summation n less than or equal to x lambda of n, right. So, let us first do, since this is capturing non-zero values only at prime powers. So, we do two things. First, now prime powers could be primes as well as higher powers of prime. So, first let us just write down the primes. Distribute this sum into two smaller sums. One is just going over primes, log p, plus the other sum is, okay, first you run over all the k greater than or equal to 2, and then for each k greater than or equal to 2, you are running over all those primes p such that p raised to the k is less than or equal to x, and for each such case you are just picking up log p. So, this is your original function theta of x. What happens over here? This is again going from k is at least 2, and the inner sum for each such k, the inner sum is running over all those primes which are less than or equal to x raised to the 1 by k log p. So, this is also this sum is also a theta function in disguise, except that this is theta of x raised to the 1 by k. So, this psi of x can be written as a combination of certain values of the theta function. And now, what happens? This is equal to theta of x. So, I am just going to focus on this part. The idea is to check that this is actually negligible. This part is, it does not create any trouble for us. So, this sum, notice you have k greater than or equal to 2, right. So, when you take 2 raised to the k, this is certainly less than or equal to any prime raised to the k, and this sum is over only going over those p to the k which are less than or equal to x. So, at the very in the most extreme scenario, 2 raised to the, at the very least 2 raised to the k must be less than or equal to x. So, in the worst possible case for k, what you have is, so 2 raised to the k is less than or equal to x. Taking logarithms, what you get is that k is less than or equal to log x over log 2. So, this is not an infinite sum. This sum is stopping at the very worst possible case at log x over log 2. So, this sum can be written as 2 less than or equal to k less than or equal to log x over log 2, and in the inner sum what you have is, if p is less than or equal to x raised to the 1 by k, it is certainly, since k is greater than or equal to 2, it is certainly less than or equal to x to the half. So, what you have is summation p less than or equal to square root x log p. This is a rough upper bound, which itself is not too bad. So, a rough estimate works. So, you have this, okay, and what is this less than or equal to? So, the inner sum, first keep the k's as they are. What is the worst possible, the maximum possible value of your inner sum? So, p is less than or equal to, the sum is running over all the primes up till root x. Okay. So, the maximum number of primes up till root x is root x. Of course, there are better bounds, but root x is fine also. Root x times log of root x. So, half of log x, right. But then k runs from 2 to this bound. So, the maximum the number of possible k's is certainly bounded above by log x over log 2, right. So, log x over log 2 times root x into half log x. So, what do you have? This is less than or equal to root x into log x whole square over some constant, which is in this case it is 2 times log 2. So, what is all this actually telling us? It is telling us that the difference between psi of x and theta of x is at most this expression over here, and in comparison to x, the growth of this function is negligible. Okay. So, to conclude this bit, what we end up getting is that what we have is that 0 is less than or equal to psi of x minus theta of x, which is less than or equal to square root of x log x whole square over 2 log 2. So, what is happening now? Note that. So, here is an exercise. This is again from basic calculus. You can show that the limit as x goes to infinity of root x log x whole square over x, this limit is equal to 0. Think about it, and in our live session we will work this out together. Should not be too hard. It is a basic calculus question, but we can discuss this if you want. So, what this is telling you is that as x goes to infinity, psi of x minus theta of x over x is going to 0 as x goes to infinity, and therefore, this tells you that if theta of x, to say that limit x going to infinity theta of x over x is equal to 1 is equivalent to saying that limit of psi of x over x is equal to 1. So, what have we got? We have got 3 different forms of writing the prime number theorem. Pi of x is asymptotic to x over log x as x goes to infinity is equivalent to saying that theta of x is asymptotic to x as x goes to infinity, which furthermore is equivalent to saying that psi of x is asymptotic to x as x goes to infinity. And this is the form. The reason we did all this work to reduce the prime number theorem to this form is that this is the form in which we eventually prove the prime number theorem. So, prime number theorem is the statement that limit x goes to infinity psi of x over x is equal to 1, where psi of x is the partial sum of the von Mangold function. And here now we study another very beautiful technique in analytic number theory to study sums of this form. I will not go into all the details right now, but let me just give you a brief idea to conclude this lecture. So, what we do is, here is a very important theme. In general, suppose you have an arithmetic function f of n and you are trying to study these partial sums, you can relate the sum. This is the genius of Riemann, and this idea was studied by Riemann, Dirichlet and many others. This is basically your analytic number theory in a nutshell. What you end up doing is, so in order to study this sum, you have to study the analytic properties of this infinite sum. And it was Riemann who first actually defined these sums for complex numbers. Okay. So, now in some region, for some for all complex numbers where real part of S is greater than some specific number, this sum will converge absolutely. Okay? And therefore, you can come up with a region on the complex plane where a closed set where this would define an analytic function. Then you bring all techniques, all that you have studied in complex analysis, and if you have forgotten, this is a time to go back and review, in particular Cauchy's integral theorem, which tells you that you can integrate, if you are trying to integrate or you are trying to derive the contour integral of a function on a certain closed contour, that is exactly equal to the sum of the residues of that complex function inside the contour. Okay? 2 minutes. Yeah. So let me just conclude by outlining what we are going to study actually in great detail later, but for that you should go back and review a little bit of complex analysis. So here is the idea. So this sum f of n turns out to be equal to, let us say that this absolutely converges, the sum is absolutely convergent for real part of S greater than some specific number sigma 0, all right. So this sum, now what it turns out to be exactly equal to the following integral. So limit as t goes to infinity 1 over 2 pi I, okay, of the integral c minus I t to c plus I t, where t is something positive and c is, so c you can choose to be anything greater than sigma 0. So you have this limit of the sum capital F of S x to the s over s ds, all right, where s is something that runs over this contour c minus I t to c plus I t, where c could be any suitable real number in the area where this sum defines a good analytic function. And finally, I want to make a quick remark about why this technique is relevant in the study of prime numbers. So this brings us to the famous Riemann Zeta function, which is the sum 1 over n to the s, n going from 1 to infinity, which is absolutely convergent in the region real part of S greater than 1. And it turns out that in exactly the same region, when you take summation n going from 1 to infinity lambda of n over n to the s, this is equal to minus zeta prime of s over zeta of s in the same region, real part of s greater than 1. And therefore, to study the partial sums n less than or equal to x lambda of n, you have to study the integral for some c which is greater than 1. So, let us take 3 by 2 plus I t, okay, of, you see the expression here is very important, minus zeta prime of s over zeta of s x raised to the s over s ds. This is the reason why the prime number theorem, or the study of distribution of prime numbers, is related to the study of zeros of the Riemann zeta function, because if zeta of s is equal to 0, then at that point s, this function has a singularity, and these singularities have to be used with the help of your Cauchy integral formula to go back to the sum. So, this was basically the technique introduced by Riemann, and before this technique there really was no progress, there was not much progress in the study of distribution of prime numbers. So, this field, this approach to number theory just cannot proceed without a good understanding of complex analysis. So, we will, of course, we will develop these ideas in detail, but these are the two main ideas I wanted to show. I wanted to tell you today that our approach to number theory is analytic. We want to use techniques from real analysis and complex analysis to study the distribution of prime numbers and distribution of a large class of arithmetic functions. The other thing that we want to learn is that there are limitations of these methods as well, and that is where methods from probability theory come into the study of arithmetic functions. So, that is something that we will introduce in the second lecture.